Well, greetings, Mr. Kolazar's class. Our new chapter is going to be called Stoichiometry. And Stoichiometry is going to be kind of bringing Chapter 9, our chemical reactions, and Chapter 10, the mole concept, together. Now, what we're going to look at is we're going to describe the amount of reactants present at the start of a chemical reaction is going to determine how much product we can actually form. And so the term stoichiometry is going to be our big term coming up. It's going to be the relationships in our balanced chemical equations. And we're going to hear the term BCE a lot, balanced chemical equation. States that they're mole ratios from balanced chemical equations and applies mole conversions. So this is why that mole has become so important to us as we're going forward. Now, kind of a quick introduction idea for stoichiometry. If we were to talk about making a bicycle, this doesn't deal with our chemical reactions, but it's going to be a similar concept. To make a bike, you need one bike frame and two wheels in order for the bicycle to be made. Now, I really can't draw a bicycle, but if you were to, it kind of, you got your handlebars there, then you got your wheels, and the wheels, and then your seat right there. But you needed two wheels to your one bike in order for that to work. So as we're going, if you wanted to make, say, 5 bikes, in order for that to work, you would need, our ratio is 1 bike frame to 2 wheels. So in order for our units to cancel out, 2 wheels would be our top conversion, what we're moving towards, and then 1 bike frame would be our bottom. So that in the end, we could see that you would need 10 wheels in order for this product to be built. Similar idea is going to be happening, except we're going to start looking at using different compounds instead. And eventually we're going to get to the fact that if maybe you had 7 bikes and you had 13 wheels, how many bikes could you total make? And so we would have to find out which one of these would actually slow down or stop our reaction from occurring, in this case building bikes. So to move into our chemical ideas of what stoichiometry is. Stoichiometry, the quantitative, meaning numbers, relationship between the amount of reactants used and the amount of products formed during a chemical reaction. So we're going to be dealing a lot with our actual numbers of materials used during our chemical reaction. This is based on the law of conservation of mass. Law of conservation of mass says we can't gain or lose material or atoms during chemical reaction. They all have to be accounted for. So the mass we start with, mass of reactants, must equal the mass of the products. We can't gain or lose mass during a chemical reaction. It all has to be accounted for. So our term stoichiometry is this concept. So many things we can get from our balanced chemical our reactions. So our relationships we're going to look into, this is the term BCE. You're going to hear it all the time coming forward. Balanced chemical equations from Chapter 9. So our idea was that first off, from a balanced chemical equation, we can come up with our word equation. We can find the number of particles reacting for producing products. They could be molecules, atoms, formula units, or ions. We can find the number of moles of each substance reacting. We can find the mass of the reacting products and what's being produced. And then our mass of the products must equal the mass of the reactants. So what we started with must equal what we ended with. So we're going to do a problem together to look through these 5 ideas. So a problem in our book says that we have methane, CH4. So that's our basic first hydrocarbon, plus oxygen, O2, produces carbon dioxide and water. Now our first thing is we need to BCE, balanced chemical equation. So to do that, our 2 is put in front of oxygen, and a 2 is put in front of water to balance this chemical equation. We do have a 1 in front of CH4 and CO2, but we don't write the 1's in. So our balanced chemical equation is where we need to start. Now once we're there, our word equation, methane plus oxygen, produces carbon dioxide and water. Now our second step, number of particles. Now particles, all 4 of these are covalently bonded. If they're covalently bonded, they're all molecules. So all of these are molecules. So number of particles, if we were to go down to the smallest form, we would have 1 molecule of CH4 would equal 2 molecules of O2 would be needed to produce 1 molecule of CO2 and 2 molecules of H2O. So we have 1 molecule to 2 to 1 to 2 is going to be our mole ratios as we're going forward, kind of like our bikes to wheels idea earlier. Now we could switch these instead, number of moles. Remember, number of moles, if you have 1 mole is 6.02 times 10 to the 23rd particles, in this case molecules. So if we could also look at it as we could have 1 mole of CH4 to 2 moles of O2 produces 1 mole of CO2 and 2 moles of H2O. Again, it's that 1 to 1 or 1 to 2 to 1 to 2 ratio that's going to be starting with or being produced. Now if we were to look at our masses of each one, we have 1 carbon and 4 hydrogens. So as we're going, 2 O2s, CO2, 2 H2Os. So the mass of each one, if we were to look at, we have 1 C at 12.01 and 4 hydrogens at 1.01. We could find out, and then 2 oxygens, but we have 2 moles of that times, and then we have 16.00 is a molecular mass. So as we're going forward, if we were to add those up, we would end up with 16.05 grams of methane, 64.00 grams of oxygen, 44.01 grams of CO2, and 34.04 or 36.04 grams of grams of H2O. Now remember, whatever number you get, you had to multiply. So 16.00 times 2, but then you had to double that beginning is where each of our numbers are coming from using our periodic table. And then if you notice, if you were to combine and add these two together and add those two total together, that the mass of the products, mass of reactants and the mass of the products are equal to one another. Our conservation of mass says that the mass to begin with must equal the mass to end with. You'll have a similar problem to work through in your assignment, so making sure if you need to look back on how you did this first one. Now, our balanced chemical equation is very important to us. So our BCE, as we're going, is going to set up what we call our mole-to-mole ratios. A ratio between the number of moles of any two of the substances in the balanced chemical equation. Now remember, these are conversion factors. Just like we've been using before, they're set up very similar. 1 foot equals 12 inches is one of our old conversion factors. Same idea is going to be happening with our conversion factors from our mole-to-mole ratios in the balanced chemical equation. And they're going to be used to convert from one substance to another the amount needed or the amount produced in our chemical reactions. So we're going to stick with this chemical equation. Methane plus oxygen produces CO2 and H2O. Now notice we don't have a number here. That number 1 is actually there, and there's no number there. 2 moles of oxygen plus 1 mole of methane produces 1 mole of carbon dioxide and 2 moles of H2O. Now we can go through to do a mole-to-mole ratio. Mole of one of the substances can react with produce a mole of any other substance. So A and B is just kind of a start and finish place. So to look at all of the relationships we can do, there's actually going to be a bunch of them. Approximately 12 is what we're going to look at here. So if we were to look at our first one says we can look at the mole-to-mole ratio between methane and oxygen. So 1 mole of methane over 2 moles of oxygen. So that's going to be our first 1:2 ratio. Now we could also look at methane to CO2. 1 mole of methane to 1 mole of CO2. And finally, 1 mole of methane to 2 moles of H2O. So we got a little bit of a setup on this first one to look through. Now the reason we want to look at these is we would use this conversion factor if we wanted to say if we started with like 5 moles of O2 times, if we start with 5 moles of O2, our moles could cancel moles, leaving us with our new unit CH4. So as we're going forward, these mole-to-mole ratios become very important. Now there are 12 of them we could do. So first off, we went CH4 to O2. Now we could go just the opposite way, and we could go backwards. So just the opposite, to go back to the CH4, instead of having on the top, it would be on the bottom. So 1 CH4 to 2 O2s. Now we could set that one up so that if we had, say, 3 CH4s, or 3 moles of CH4, the CH4 could cancel CH4, and leaving us with how many O2s, moles that we wanted. So our last of our conversions, we could start out with the O2. 2 moles of O2 to 1 mole of CO2 would be a mole-to-mole conversion. 2 moles of water equal 2 moles of oxygen would be a conversion. And moving back the other way, just the opposite, flipping those two over. So you could see our mole-to-mole conversions between those two. Depending on who's on top and who's on bottom, it's still equal to each other. And finally, to finish out, CO2 and H2O, O2, our CO2 to H2O is a 1:2 ratio. So as we're going, our mole-to-mole ratios are going to allow us that conversion factor to go between those moles as we're going forward. We're going to stop here for today. Go ahead and make sure if you have any questions for tomorrow when we begin working on our problems of looking at our mole-to-mole ratios needed from our balanced chemical equations.